Good day, everyone. We are the last group to present Unit 12 Decision Analysis. First, an overview of our topic. Learning outcomes. Describe the payoff tables and decision trees and provide a structure for the decision problem. Illustrate the fundamentals of decision analysis. Discuss the use of Bayes' theorem for calculating possibilities of future events. Decision analysis. Business analytics is about making better decisions. The tools and techniques that have been introduced previously are designed to aid a decision maker in analyzing existing data, predicting future behavior, and recommending decisions. This can be used to develop an optimal strategy when a decision maker is faced with several decision alternatives and an uncertain or risk filled pattern of future events. Here is one example of application for decision analysis. Phytoparm's new product and research development discusses the use of decision analysis to manage Phytoparm's pipeline of pharmaceutical products, which have long development times and relatively high levels of uncertainty. Even when a careful decision analysis has been conducted, the uncertain future events mean that the final outcome is not completely under the control of the decision maker. In some cases, the selected decision alternative may provide good or excellent results. Here is another example. Federal agencies in the United States have used decision analysis to evaluate the potential risks from terrorist attacks and to recommend counterterrorism strategies. The state of North Carolina used decision analysis in evaluating whether to implement a medical screening test to detect metabolic disorders in newborns. In other cases, a relatively unlikely future event may occur, causing the selected decision alternative to provide only fair or even poor results. The risk associated with any decision alternative is a direct result of the uncertainty associated with the final outcome. A good decision analysis includes careful consideration of risk. Let us now move on to problem formulation. First, we begin with a verbal statement of the problem. Second, we then identify the decision alternatives. Third, the uncertain future events, referred to as chance events. Fourth, the outcomes associated with each combination of decision alternative and chance event outcome. Now we all have that covered. Let us move on to an example. Pittsburgh Development Corporation, or PDC, purchased land that will be the site of a new luxury condominium complex. The location provides a spectacular view of downtown Pittsburgh and the Golden Triangle, where the Allegheny and Monongahela rivers meet to form the Ohio River. PDC plans to price the individual condominium units between $300,000 and $1,400,000. PDC commissioned preliminary architectural drawings for three different projects, one with 30 condominiums, one with 60 condominiums, and one with 90 condominiums. The financial success of the project depends on the size of the condominium complex and the chance event concerning the demand for the condominiums. The statement of the PDC decision problem is to select the size of the new luxury condominium project that will lead to the largest profit given the uncertainty concerning the demand for the condominiums. We may now use them as D sub 1 is equal to a small complex with 30 condominiums, D sub 2, a medium complex with 60 condominiums, D sub 3, a large complex with 90 condominiums. When asked about the possible demand for the condominiums, PDC's president acknowledged a wide range of possibilities, but decided that it would be adequate to consider two possible chance event outcomes: a strong demand and a weak demand. In decision analysis, the possible outcomes for a chance event are referred to as states of nature. The states of nature are defined so that they are mutually exclusive, meaning no more than one can occur, and collectively exhaustive, meaning that at least one must occur. Thus, one and only of the possibility states of nature will occur. We may now label them as S sub 1 for strong demand for the condominiums and S sub 2, meaning weak demand for the condominiums. Let us now move on to payoff tables. Given the three decision alternatives and the two states of nature, which complex size should PDC choose? To answer this question, PDC will need to know the outcome associated with each possible combination of decision alternative and state of nature. In decision analysis, we refer to the outcome resulting from a specific combination of a decision alternative and a state of nature as payoff. A table showing payoffs for all combinations of decision alternatives and states of nature is a payoff table. Here is the table showing payoffs for all combinations of decision alternatives and states of nature. We will be expressing these numbers in millions. Because PDC wants to select the complex size that provides the largest profit, profit is used as the outcome. The payoff table with profits in millions of dollars is shown in Table 12.1. Note, for example, that if a medium complex is built and demand turns out to be strong, a profit of $14 million will be realized. We will use the notation V sub ij to denote the payoff associated with decision alternative I and state of nature j. Using table 12.1, V sub 31 is equal to 20. It indicates that a payoff of $20 million occurs if the decision is to build a large complex, D sub 3, and the strong demand state of nature, S sub 1, occurs. Similarly, V sub 32 is equal to negative 9. It indicates a loss of $9 million if the decision is to build a large complex, D sub 3, and the weak demand state of nature, S sub 2, occurs. We will now move on to decision trees. A decision tree provides a graphical representation of the decision-making process. Figure 12.1 presents a decision tree for the PDC problem. Note that the decision tree shows the natural or logical progression that will occur over time. First, PDC must make a decision regarding the size of the condominium complex, D sub 1, D sub 2, or D sub 3. Then, after the decision is implemented, either state of nature's S sub 1 or S sub 2 will occur. The number at each endpoint of the tree indicates the payoff associated with a particular sequence. For example, the topmost payoff of 8 indicates that an $8 million profit is anticipated if PDC constructs a small condominium complex, D sub 1, and demand turns out to be strong, S sub 1. The next payoff of 7 indicates an anticipated profit of $7 million if PDC constructs a small condominium complex, D sub 1, and demand turns out to be weak, S sub 2. Thus, the decision tree provides a graphical depiction of the sequences of decision alternatives and states of nature that provide the 6 possible payoffs for PDC. The decision tree in Figure 12.1 shows four nodes, numbered 1 to 4. Nodes are used to represent decisions and chance events. Squares are used to depict decision nodes. Circles are used to depict chance nodes. Thus, node 1 is a decision node, and nodes 2, 3, and 4 are chance nodes. The branches connect the nodes. Those leaving the decision node correspond to the decision alternatives. The branches leaving each chance node correspond to the states of nature. The outcomes, payoffs, are shown at the end of the states of nature branches. We now turn to the question: how can the decision maker use the information in the payoff table or the decision tree to select the best decision alternative? Several approaches may be used and are covered in the remaining sections of this chapter.
Next is decision making with and without probabilities. First, let's discuss what decision making without probabilities is. Here, we consider approaches to decision making that do not require knowledge of the probabilities of the states of nature. These approaches are appropriate in situations in which the decision maker has little confidence in his or her ability to assess the probabilities, or in which a simple best case and worst case analysis is desirable, because different approaches sometimes lead to different decision recommendations. The decision maker needs to understand the approaches available and then select the specific approach that, according to the decision maker's judgment, is the most appropriate. There are three decision making approaches. Those are maximax or optimistic approach, maximin, conservative or pessimistic approach, and minimax regret. Optimistic approach or maximax approach evaluates each decision alternative in terms of the best payoff that can occur. The decision alternative that is recommended is the one that provides the best possible payoff. For a problem in which maximum profit is desired, the optimistic approach would lead the decision maker to choose the alternative corresponding to the largest profit. For problems involving minimization, this approach leads to choosing the alternative with the smallest payoff. On the other hand, conservative or maximum approach evaluates each decision alternative in terms of the worst payoff that can occur. The decision alternative recommended is the one that provides the best worst possible payoffs. For a problem in which the output measure is profit, the conservative approach would lead the decision maker to choose the alternative that maximizes the minimum possible profit that could be obtained. For problems involving minimization, this approach identifies the alternative that will minimize the maximum payoff. While minimax regret, it is an approach to decision making that is neither purely optimistic nor purely conservative. To learn more about decision analysis without probabilities, let us watch this video.
Welcome. In this brief video, we will be discussing decision making without probabilities. In this first part, we will consider the maximax or the optimistic approach, the maximin, also known as conservative or pessimistic approach, and the minimax regret approach to decision making. The table seen here is referred to as a payoff table or decision table. The alternatives on the left here in the rows are referred to as decision alternatives. They are the options available for the decision maker to choose from. We will assume that the decision maker can only choose one of these alternatives: invest in bonds, stocks, or mutual funds. In the columns, we have the economic conditions. Since the decision maker does not have control over these, we refer to them as states of nature or outcomes. The values in the table are called payoffs. There could be profit, cost, distance, time, and so on. In this example, we treat them as profits. The Maximax or optimistic approach. Using this optimistic approach, we choose the alternative with the best possible payoff. Looking at bonds, the best payoff is 45, the best is 70 for stocks, and the best is 53 for mutual funds. The overall best is 70, therefore the decision is to invest in stocks. The Maximin or conservative approach. Using this pessimistic approach, we choose the alternative with the best of the worst payoffs. We first choose the worst payoff in each alternative and then choose the best of the worst. Looking at bonds, the worst payoff is 5, the worst is minus 13 for stocks, and the worst is minus 5 for mutual funds. The best of this is 5. Therefore, the pessimistic or conservative approach is to invest in bonds. The Minimax regret approach. Using this approach, we choose the alternative with the minimum of all maximum regrets across all alternatives. Regret, also known as opportunity loss, is the difference between the best payoff in a particular state of nature and the actual payoff received. For example, if the economy is growing, the best payoff is 70. If we happen to have invested in bonds, then the regret will be 70 minus 40, which is 30. If we invested in stocks, then there is no regret. If we invested in mutual funds, then the regret is 70 minus 53, which is 17. Again, if the economy is stable, the best payoff is 45. So if we invested in bonds, there is no regret. The regret is 45 minus 30 if we invested in stocks. If we invested in mutual funds, there is also no regret. For declining economy, the best payoff is 5. If we invested in bonds, there is no regret. If we invested in stocks, the regret is 5 minus negative 13, which is 18. If we invested in mutual funds, the regret is 5 minus negative 5, which is 10. Here is the regret table. Since the decision is to be made based on minimax regret, we first determine the maximum regret for each alternative and then choose the minimum. For bonds, the maximum regret is 30. For stocks, it is 18, and for mutual funds, it is 17. The minimum of these maximum regrets is 17. The decision is to invest in mutual funds. See you in part 2. Thanks for watching.
Now, let's proceed to decision making with probabilities. In many decision making situations, we can obtain probability assessments for the states of nature. When such probabilities are available, we can use the expected value approach to identify the best decision alternative. Let us define EV or expected value. According to Investopedia, expected value or EV is an anticipated value for an investment at some point in the future. In statistics and probability analysis, the expected value is calculated by multiplying each of the possible outcomes by the likelihood each outcome will occur and then summing all those values. Next is risk analysis. It helps the decision maker recognize the difference between the expected value of a decision alternative and the payoff that may actually occur. A decision alternative and a state of nature combine to generate the payoff associated with the decision. The risk profile for a decision alternative shows the possible payoffs along with their associated probabilities.
Welcome. In this tutorial, we will discuss decision-making with probabilities. Some refer to this as decision-making under risk. We will be covering the expected value or expected monetary value and the expected value of perfect information. We will be using this payoff table where payoffs are profits and the probabilities of the states of nature are 0.2, 0.5, and 0.3 respectively. The expected monetary value. This is a weighted average of the payoffs for a decision alternative. The weights are the probabilities of the different states of nature. For bonds, the expected value is calculated as 0.2 times 40 plus 0.5 times 45 plus 0.3 times 5, which equals 32. For stocks, the expected value is 0.2 times 70 plus 0.5 times 30 plus 0.3 times negative 13, which equals 25.1. For mutual funds, the expected value is 0.2 times 53 plus 0.5 times 45 plus 0.3 times negative 5, which equals 31.6. The best expected value is 32, therefore the decision is to invest in bonds.
Now let's proceed to decision analysis with sample information. Decision analysis with sample information. Sample information. Additional information that is obtained through experiments about the states of nature. Examples of experiment or studies: raw material sampling, product testing, and market research studies. Some additional terms related to decision analysis. The first one is the preliminary or prior probability. Assessments for the states of nature that are the best probability values available prior to obtaining additional information. The second one is the posterior probabilities. These are revised probabilities after obtaining additional information. Decision strategy. It is a sequence of decision and chance outcomes where the decisions chosen depend on the yet to be determined outcomes of chance events. The approach used to determine the optimal decision strategy is based on the rollback of the expected values in a decision tree using the following steps. The first step is the at chance nodes. Compute the expected value by multiplying the payoff at the end of each branch by the corresponding branch probabilities. The second step, at decision nodes, select the decision branch that leads to the best expected value. This expected value becomes the expected value at the decision node. And now, to learn more about the decision analysis, let's all watch the video.
Welcome to this decision analysis tutorial for constructing decision trees. We will be constructing a basic decision tree. We will also be making decisions using the expected value approach. We will be constructing a decision tree using this payoff table, where payoffs are profits and the probability of the states of nature are 0.4 and 0.6 respectively. Decision trees use two types of nodes: a square or rectangle node called decision node, from which decision alternative branches will originate, and a circle node called chance node, from which states of nature or outcome branches will emanate. The chance node is also referred to as an outcome node or event node. Now let's construct a decision tree for this payoff table. We first draw a decision node with branches coming out of the decision node representing decision alternatives. Next, we draw the chance node or outcome node with respective states of nature or outcomes, as it can be seen here for stocks. The payoffs are placed at the end of the branches, as you can see, 70 and negative 13 for stocks. We do the same for mutual funds and for bonds. Notice that the payoff is 20 for bonds, irrespective of the state of nature. Therefore, we really don't need to repeat 20. We simply need to draw a single branch from bonds with a payoff of 20. Now let's solve the decision tree. Solving the decision tree is also known as folding back the decision tree. In essence, we are going to calculate the expected values and then choose the best. For stocks, the expected value is calculated as 0.4 times 70 plus 0.6 times negative 13, which is 20.2. So we just usually write the 20.2 on the chance node for stocks. We do the same for mutual funds. The expected value is 0.4 times 53 plus 0.6 times negative 5, which is 18.2. We also write that on the chance node for mutual funds. For bonds, no calculation is required. We can only expect a payoff of 20 for bonds. Now, comparing the three values, 20.2, 18.2, and 20, the best expected value is 20.2. We usually just place that value close to the decision node. Therefore, the decision is to invest in stocks. Thanks for watching.
And now let's proceed to the expected value of sample information. This estimates the value of a decision to collect additional sample information. Typically, additional research reduces, rather than eliminates uncertainty, meaning perfect information is not available. Therefore, expected value of sample information, or EVSI, can be utilized to help determine the optimal research design or the study population comparison to be tested and the sample size to maximize the reduction in uncertainty and the value to the society of conducting the study. The last one is the expected value of perfect information, or EVPI. A special case of gaining additional information related to a decision problem is when the sample information provides perfect information on the states of nature. In other words, consider the case where the market study undertaken by a company would determine exactly which state of nature will occur. And now, let's proceed on watching the video to learn about the EVSI and the EVPI.
Welcome to this decision tree tutorial for expected value of sample information. In this tutorial, we'll be constructing a decision tree with sample information. We will also be calculating the expected value of sample information. We will be using this payoff table where payoffs are profits. This is the decision tree for the payoff table. The expected value for stocks is calculated as 20.2. For mutual funds, it is 18.2, and for bonds, it is 20. The best of the expected values is 20.2, therefore the decision is to invest in stocks. Now, suppose there is an economic consultant that can provide additional information about the states of nature or outcomes, and this consultant has some success history. We now have an additional decision situation. Should we hire this consultant or not? If we don't hire the consultant, we will stick to our initial decision to invest in stocks. If we decide to hire the consultant, then we will consider two factors. Number one, how successful has the consultant's information been in the past? And number two, how much does it cost to hire the consultant? Here is a reduced version of our decision situation. Suppose if we hire the consultant, he or she could give a positive or a negative report about economic conditions. This report from additional information is often referred to as prediction, forecast, or result. Suppose the probability of the consultant giving a positive report is 0.44. This will mean that the probability of a negative report is 0.56. Since these are probabilities, we represent them using a chance node with positive and negative branches. Now suppose, given a positive report, the probability of a growing economy is 0.59 and the probability of growth given a negative report is 0.25. This means that the probability of decline given positive report is 1 minus 0.59, which is 0.41, and the probability of decline given negative report is 1 minus 0.25, which is 0.75. These probabilities are called posterior probabilities. We will discuss them in detail in the next video. So if the report is positive, we paste the original tree here with posterior probabilities 0.59 and 0.41. We do the same for negative report with probabilities 0.25 and 0.75. The chance nodes have now been labeled 1 to 5 for reference purposes as we calculate the expected values. The expected value for node 1 is 0.59 times 70 plus 0.41 times negative 13, which equals 35.9. In similar fashion, we calculate the expected value for node 2, for node 3, and for node 4. Now, if the report is positive, the best expected value is 35.97 from stocks. And if the consultant's report is negative, the best expected value is 20 from bonds. Next, we calculate the expected value for node 5, which is 0.44 times 35.97 plus 0.56 times 20, which gives 27.0268. The expected value of sample information estimates the value of information supplied by the consultant. Sample information is also known as imperfect information. So the expected value of sample information, EVSI, is calculated as EV with SI minus EV without SI. EV with SI is the expected value with sample information, that is, expected payoff if the consultant is hired, without paying the consultant. EV without SI is the expected value without sample information, that is, the best expected payoff if the consultant is not hired. In this case, EV with SI is 27.0268 and EV without SI is 20.2. Therefore, EVSI is the difference between the two values, which gives 6.8268. Now let's see how to use EVSI to determine the best decision strategy. Suppose the cost to hire the consultant is 7.2, which is higher than EVSI. That is, the fee is higher than the value added by the consultant. And so, the decision strategy will be not to hire the consultant. As a result, we will stick to our initial decision and invest in stocks. On another note, suppose the consultant's fee is 3.5, which is less than EVSI. Then the strategy will be stated as follows. Hire the consultant. If the consultant's report is positive, invest in stocks. If the consultant's report is negative, invest in bonds. And that's how to calculate and use the EVSI to determine the best decision strategy. Expected value of perfect information. The expected value of perfect information, EVPI, is the maximum amount you will be willing to pay for additional information about a decision problem. That is, if we have perfect information about the state of nature before the decision is made, how much is this information worth? The formula for the expected value of perfect information is EVPI equals EV with PI minus EV without PI. EV with PI is the expected payoff if perfect information about the state of nature is known. EV without PI is the expected value without perfect information, which is the best expected payoff without additional information. That is, the maximum EMV. The maximum EMV was determined to be 32 earlier. To calculate EV with PI, expected value with perfect information, we choose the best payoff for each state of nature and multiply them by the probability of their state of nature and add the results. So EV with PI is 70 times 0.2 plus 45 times 0.5 plus 5 times 0.3, which equals 38. The expected value with perfect information is 38. As calculated earlier, the expected value without perfect information, or maximum EMV, is 32. Therefore, EVPI is 38 minus 32, which is 6. So if we have perfect information about the states of nature before the decision is made, the expected value of that perfect information will be 6. And that's how you calculate EVPI. Thanks for watching.
Next, we'll move on to computing branch probabilities with Bayes' theorem. What is Bayes' theorem? It is a theorem that enables the use of sample information to revise prior probabilities. It also relates to conditional probabilities, the probability of one event given the known outcome of a possibly related event. The PDC decision tree is shown again in figure 12.10. Let F be our favorable market research report, U be our unfavorable market research report, and state of nature 1 being our strong demand and state of nature 2 being the weak demand. At chance node 2, we need to know the branch probabilities of our favorable market research report and the probability of our unfavorable market research report. At chance nodes 6, 7, and 8, we need to know the branch probabilities, the probability of state of nature 1 given a favorable market research report, and the probability of state of nature 2 given that the market research report was favorable. These two branch probabilities indicate a conditional probability because we are interested in the probability of a particular state of nature conditioned on the fact that we receive a favorable market report. So the probability of state of nature 1 given a favorable market research report and the probability of state of nature 2 given a favorable market research report are referred to as posterior probabilities because they are conditional probabilities based on the outcome of the sample information. At chance nodes 9, 10, and 11, we need to know the branch probabilities of state of nature 1 given that there is an unfavorable market research report and state of nature 2 given that there is an unfavorable market research report. Note that these are also posterior probabilities, denoting the probabilities of the two states of nature given that the market research report is unfavorable. Finally, at chance nodes 12, 13, and 14, we need the probabilities for the states of nature 1 and 2 if the market research study is not undertaken. In performing the probability computations, we need to know PDC's assessment of the probabilities for the two states of nature, which are the prior probabilities as discussed earlier. In addition, we must know the conditional probability of the market research outcomes, which is the sample information, given each state of nature. For example, we need to know the conditional probability of a favorable market research report given that the state of nature is strong demand for the PDC project. To carry out the probability calculations, we will need conditional probabilities for all sample outcomes given all states of nature. That is the probability of having a favorable market research report given that the state of nature is strong, the probability of having a favorable market research report given that the state of nature is weak, the probability of having an unfavorable market research report given that the state of nature is strong, and the probability of having an unfavorable market research report given that the state of nature is weak. These conditional probabilities are assessments of the accuracy of the market research. They are often estimated using historical performance of previous market research reports. For example, the probability of having a favorable market research report, given that the state of nature is strong, may be estimated via the historical frequency of the strong demand being associated with a market research report that was favorable. In the PDC problem, we assume that the following assessments are available for these conditional probabilities. Note that the preceding probability assessments provide a reasonable degree of confidence in the market research study. If the true state of nature is strong, the probability of a favorable market research report is 0.90, and the probability of an unfavorable market research report is 0.10. If the true state of nature is weak, the probability of a favorable market research is 0.25, and the probability of an unfavorable market research report is 0.75. One reason for a 0.25 probability of a potentially misleading favorable market research report for state of nature S2, meaning that is weak, is that when some potential buyers first hear about the new condominium project, their enthusiasm may lead them to overstate their real interest in it. A potential buyer's initial favorable response can change quickly to a no thank you when later faced with the reality of signing a purchase contract and making a down payment. In the following discussion, we present a tabular approach as a convenient method for carrying out the probability computations. The computations for the PDC problem based on a favorable market research report are summarized in Table 12.7. The steps used to develop this table are as follows. Step 1. In column 1, enter the states of nature. Step 2. In column 2, enter the prior probabilities for the states of nature. Step 3. In column 3, enter the conditional probabilities of a favorable market research report given each state of nature. Step 4. In column 4, compute the joint probabilities by multiplying the prior probability values in column 2 by the corresponding conditional probability values in column 3. Step 5. Sum the joint probabilities in column 4 to obtain the probability of a favorable market research report. Step 6. Divide each joint probability in column 4 by 0.77 to obtain revised or posterior probabilities. Having the state of nature being strong given that the favorable market research report, and the state of nature being weak given that the favorable market research report. Table 12.7 shows that the probability of obtaining a favorable market research report is 0.77. In addition, the probability of having the state of nature being strong given that the favorable market research report is equal to 0.94, and the probability of having the state of nature being weak given that the favorable market research report is equal to 0.06. In particular, note that a favorable market research report will prompt a revised or posterior probability of 0.94 that the market demand of the condominium will be strong. The tabular probability computation procedure must be repeated for each possible sample information outcome. Table 12.8 shows the computations of the branch probabilities of the PDC problem based on an unfavorable market research report. Note that the probability of obtaining an unfavorable market research report is 0.23. If an unfavorable report is obtained, the posterior probability of a strong market demand is 0.35, and of a weak market demand is 0.65. The branch probabilities from tables 12.7 and 12.8 were shown on the PDC decision tree in figure 12.6. The tabular method can be used directly to compute the branch probabilities in the decision tree. Alternatively, equation 12.5 provides a general formula for Bayes' theorem for computing posterior probabilities. To perform the Bayes' theorem calculations for the probability of having the state of nature being strong, given that the unfavorable market research report with equation 12.5, we replace B with U unfavorable report and A with the state of nature being strong in 12.5, so that we have 0.10 times 0.80 divided by 0.10 times 0.80 plus 0.20 times 0.75 is equal to 0.35, which provides the same value as the tabular approach used to generate the values in table 12.7. The discussion in this section shows an underlying relationship between the probabilities on the various branches in a decision tree. It would be inappropriate to assume different prior probabilities without determining how these changes would alter the favorable and the unfavorable as well as the posterior probabilities.
Last chapter of Unit 12 entitled Utility Theory. Utility theory provides a methodological framework for the evaluation of alternative choices made by individuals, firms, and organizations. It refers to the satisfaction that each choice provides to the decision maker. Utility theory assumes that any decision is made on the basis of the utility maximization principle, according to which the best choice is the one that provides the highest utility or satisfaction to the decision maker. So how is utility measured? This video that I will show you will give an example of data using the utility theory model.
This question tells us that Haley must choose between gamble A and gamble B, and also between gamble C and gamble D. It says which of the following preferences is consistent with the expected utility model. And it goes on to give us some different answer choices, but before we look at those, let's take a look at the expected wealth of each gamble. Now we don't have to do that to answer this question, but it is going to help us organize our thoughts. So expected wealth of gamble A is $1,450. The expected wealth of gamble B we find to be $1,200. The expected wealth of gamble C we find to be $600. And the expected wealth of gamble D we find to be $850. So now that we've found those expected wealths, let's take a look at our answer choices. Answer choice A says that we prefer gamble B over gamble A, and that we prefer gamble C to gamble D. Well, this is the right answer. Before we talk about why, let's talk about why the other answer choices aren't consistent with the expected utility model. Answer choice B says we prefer gamble A to B, and we prefer gamble C to D. So let's take a look at gamble A. Gamble A, we have a 15% chance of getting 0, a 70% chance of getting 1,000, and a 15% chance of getting 5,000. Comparing that to gamble B, that has a 0% chance of getting 0, 95% chance of getting 1,000, and a 5% chance of getting 5,000, we notice that gamble A has the higher probability on each extreme outcome. So the extreme outcomes here are $0 and $5,000, and in both cases, gamble A's probability is higher. So gamble A is the riskier gamble. Let's take a look at gamble C compared to gamble D. Gamble C and gamble D are similar to gamble A and B. Gamble C is similar to gamble B because it has the lower chance of each extreme outcome. Gamble D is very similar to gamble A because it has the higher chance of each extreme outcome. So gamble D is riskier than gamble C. Even though we see that gamble A and D have the highest expected payoffs relative to the other gamble that we're comparing it to, they're the riskier gambles. So option choice B that says that we prefer A to B, so we prefer a riskier gamble to a not so risky gamble, and then we prefer C to D, so we prefer a not so risky gamble to a riskier gamble, this can't be right. This is inconsistent with the expected utility model. So we can get rid of that answer choice. Option choice C says we're indifferent between A and B, but we prefer C to D. This is saying we're indifferent between a riskier gamble and a not so risky gamble, but we prefer a not so risky gamble to a risky gamble. That's just not consistent with the expected utility model either, so we can get rid of that. Option choice D, for the same reasons, is not consistent. Let's take a look at option choice A. It says we do prefer B to A and we prefer C to D. And this is consistent because B, as we said, is a not so risky gamble, so maybe this represents a very risk-averse person. And this is very consistent because option B is less risky and we prefer that to option A, and option C is less risky and we prefer that to option D. So this answer is right because both of these gambles that we prefer are less risky, and therefore this could very well represent somebody who's very risk-averse.
Now, let's talk about utility and decision analysis. Utility is a way of accounting for a decision maker's risk tolerance. This is where the decision maker always chooses the alternative for which the expected value of the utility is maximum. And for decision analysis, it is a systematic, quantitative, and visual approach to addressing and evaluating the important choices that businesses sometimes face. A decision maker who would choose a guaranteed payoff over a lottery with a superior expected payoff is a risk avoider. Now, what is the connection between utility and decision analysis? If that assumption is accepted in the utility theory, it can be used to predict or prescribe the choice that the decision maker will make or should make among the available alternatives. Now here are the following steps state in general terms the procedures used to solve the software incorporation investment problem. First step is to develop a table using monetary values. Step 2. Identify the best and worst payoff values in the table and assign each a utility with U, best payoff, and U, worst payoff. So as you can see here, the utility of negative $50,000 is equals to U, negative 50,000 equals to 0, which means that that is the worst payoff. And utility of $50,000 is equals to U times 50,000 is equals to 10, which is the best payoff. Now for step 3, for every other monetary value M in the original payoff table, do the following to determine its utility. So letter A, define the lottery such that there is a probability of P of the best payoff and a probability 1 minus P of the worst payoff. So in here, the lottery, Swofford obtains a payoff of $50,000 with a probability P and the payoff of negative $50,000 with the probability of 1 minus P. Letter B, determine the value of P such that the decision maker is indifferent between a guaranteed payoff of M and the lottery defined in step 3, letter A. So let's say for example that our P is equals to 0.95. Now for letter C, calculate the utility of M as follows. Now let's say that the letter U represents utility. So U is equals to P times utility of best payoff plus 1 minus P times the utility of worst payoff. Now you just have to substitute the corresponding amount to each letters or words. Now for the best payoff, which is $50,000, and the worst payoff, which is negative $50,000. So as we said earlier, that P is equals to 0.95, and the utility of best payoff is equals to 10, and the utility of worst payoff is equals to 0. Now you just have to perform the given operations to come up with a sum of 9.5. But obviously, as you can see, If we had started with a different assignment of utilities for a payoff of the $50,000 and the negative $50,000, then the result would have been a different to the utility of $30,000. Now let's say, for example, so in here, if we had started that the utility of the $50,000 is 100 and the utility for the negative $50,000 is 10, then the utility of the $30,000 payoff would be 95.5. A big difference, right? So we must conclude that the utility assigned to each payoff is not unique, but each payoff merely depends on what our initial choice or the decision maker's initial choice for the utilities of the best and worst payoff. Now let's go to step 4. Convert each monetary value in the payoff table to a utility. So of course, after the $30,000, next is the $20,000, 0, negative $20,000, and so on. So the table depends on the monetary value that each decision maker has. So you can see the difference or the indifference value of P and its corresponding utility. And now for step 5. Apply the expected utility approach to the utility table developed in step 4 and select the decision alternative with the highest expected utility. So you can see the decision alternative, which is investment A, investment B, and do not invest. Now, the expected utility for each of the decision alternatives in this offered problem is in the following. Investment A or D1 is equals to 7.35, investment B or D2 is equals to 6.55, and do not invest or D3 is equals to 7.50. That can be seen that it is the higher among the rest. But take note that optimal decision using the expected utility approach is D3 or do not invest. So for the viewpoint of the risk avoiders or those people who wanted to avoid risk as much as possible, they will most likely pick D3 because they don't need to risk their money anytime.
Utility function is a representation to define individual preferences for goods or services beyond the explicit monetary value of those goods or services. In other words, it is a mathematical function that represents individuals' choice or a calculation for how much someone desires something and its relative. So, in all cases, the utility that the decision maker gets from selecting a specific choice is measured by a utility function U, which is a mathematical representation of the decision maker's system of preferences such that use of X is greater than use of Y, where choice X is preferred over choice Y, or use of X is equal to use of Y, where choice X is indifferent from choice Y, or both choices are equally preferred. Here's an example video of using utility functions.
When we talked about influence diagram, we included in the influence diagram nodes that represent the agent's utility function. And those utility functions, we said, indicate an agent's preferences regarding the state of the world or different aspects of the state of the world. What are these utility functions and where do they come from? So, utility functions are necessary for our ability to compare complex scenarios that involve uncertainty or risk. It's not difficult for a person to say that they prefer an outcome where they get 4 million to one where they prefer 3 million. But it's not quite as easy to encode a more complicated preference that allows us to compare the utility of these two lotteries, as they're called, where the one on the left gives the agent $4 million with probability 0.2, and the one on the right gives the agent $3 million with probability 0.25. Which of those lotteries do we prefer if we had to make that decision? it turns out that the way to formalize the decision-making process of an agent in this type of scenario is by ascribing a numerical utility to these different outcomes, to the outcome of 4 million, to the outcome 3 million, and to the outcome of $0, and then we can use the principle of maximum expected utility to decide between these two different lotteries. Specifically, we can then compare 0.2 times the utility of the outcome 4 million plus 0.8 to the utility of the outcome $0 versus the converse, which is 0.25 versus the expected utility for the second lottery, which is 0.25 times the utility of $3 million plus 0.75 times the utility of $0. And we can compare these two expressions and decide whether we prefer the one on the right, the one on the left, the one on the right, or they're equally good in our view. Now, it might be natural to assume that utility should be linear in the amount of payoff that we get, so that $5 is preferred about half as much as $10. It turns out that that's actually not the case for most people, and one example of that is this decision-making situation over here, where on the left the agent has the option of getting $4 million with probability 0.8, and on the right they have the option of getting $3 million with certainty. Most people tend to prefer the lottery on the right. But if one computes the expected payoff of these two different lotteries, we can see that the expected payoff over here is 4 million times 0.8, which is 3.2 million. Whereas on the right, we have an expected payoff of 3 million. So the expected payoff on this side is higher, and nevertheless, people prefer the lottery on the right. Another example, very famous example of this type of preference is what's called the St. Petersburg paradox. St. Petersburg paradox is an imaginary game that one can play where a fair coin is tossed repeatedly until it comes up heads for the first time. And if it comes up heads for the first time on the nth toss, you get 2 to the n dollars. So what's the expected payoff in this case? Well, the probability that it comes up heads on the first toss is half, and then you get $2. The probability that it comes up heads for the first time is a quarter, and the payoff here is $4. Third toss is eighth times $8, and it's easy to see that the expected payoff over here is infinite. So in principle, people might be willing to pay any amount to play this game because their expected payoff is bigger than any amount that they would be paying to play. But the fact is that for most people, the value of playing this game is approximately $2, which is a strong indication that their preferences are not linear in the amount of money that they earn. So let's try and quantify that using this notion, which is called a utility curve. The utility curve in this case has as the x-axis the dollar amount that you get, and on the y-axis the utility that an agent ascribes to that. And now let's compare a few different scenarios here. So first, let's look at the utility of getting $500. So if we go up from 500 to the utility curve, we can see that the utility of this outcome is going to fall over here. So this is going to be the utility of $500. But now let's look at a situation that involves some risk. So let's look at a set of lotteries where I get $0 with probability 1 minus p and $1,000 with probability p. Because of the linearity of expected utility, all of these lotteries are going to sit on this line over here, where depending on the value of p, I have a different weighted combination between getting the utility of $0 and the utility of $1,000. So for high values of p close to 1, we would be sitting on this side of the curve, and otherwise, for example, for low values of p, we would be sitting close to here. Specifically, what happens if we look at the probability p equals 0.5? Well, in that case, we would have this point on the curve over here. Now, the important thing to notice is that the utility of this point where I get $1,000 probability 50% and $0 probability 50%, that utility in this example is considerably lower than the utility of $500. So I prefer to get the $500 for certain, which is what most people would say. Now, if we look at what the lottery is worth, that is the risky version, we can see that that sits over here and might, for example, be corresponding to getting $400 with certainty. So that $400 is called the certainty equivalent of this lottery over here. That is, it's the amount that you'd be willing to trade for this lottery in terms of getting that money for certain. The difference between these two numbers, the expected reward and the utility of that lottery, is called the insurance premium or the risk premium. And it's called that because that's where insurance companies make their money, because of a person's willingness to take less money with certainty over a more risky proposition. So we can see that this kind of a curve that has this shape, this concave shape, is representing a risk profile which is risk averse. That is, a person is willing to pay for taking less risk. Other profiles would of this curve would represent different behaviors. So, for example, if the utility was linear in the reward, that would be a behavior that was called risk neutral. Conversely, if we had a curve that looked like this, which is a convex function, that would be risk seeking. And risk-seeking behavior occurs, for example, in Las Vegas, where one is willing, or in other gambling situations, where one is willing to actually take a loss in terms of the expected reward for the small chance of getting a really high payoff. Now, it turns out that people often have a utility curve that looks like the following. So if the x-axis is the amount of money that we get, and we arbitrarily place the 0 point over here, which is at one's current state, and we ask how much do you prefer to earn money and how much do you prefer to lose money, what's your utility for these different changes to one's state, we can see that one's preferences for earning money typically exhibit a form of diminishing returns, which gives us this concave utility curve, which suggests risk-averse behavior in the sense that we would prefer a certain amount of, we would prefer to get money with certainty relative to the expected, relative to the payoff equivalent uncertain lottery. Now, on the negative side of the spectrum, many people exhibit some kind of behavior that is actually more risk-seeking, which means that many people would prefer a small probability of a large loss relative to a small loss that you get with certainty. And that's a behavior that one often sees. More importantly, in this region of the space, which is close to one's current state, the behavior is often risk neutral. That is, small losses or small gains on the order of a small number of dollars, and of course it depends on one's baseline, are often something that you don't really care about having the uncertainty, and the expected payoff is often very close to the utility of the expected payoff.
Last is exponential utility function, that defined as a class of utility function that's used in many financial investment decisions. An exponential utility function has just one adjustable numerical parameter called the risk tolerance, and there are straightforward ways to discover an appropriate value of this parameter for a company or individual.
In this video, I'm going to show you how to make an exponential trend line in Excel, and then talk about the different ways that Excel represents exponential functions compared to the way your book and we typically use in this class. So here I have some data. My T represents time in years since 1990, and my R represents revenue in billions of dollars for each of the years since 1990. And the first step, whenever you want to make a trend line, is you highlight all of your data, and then I'm going to insert a scatter plot, and just pick the basic one without any lines connecting the dots. And let me change my layout and get some places to title this. So this is years since 1990. This is revenue in billion dollars. And I believe this data represents Compaq's revenue. So good enough. And then I'm going to delete that little label to make my graph look bigger. Alright, so that's always our first step, to get our trend line. Then I'm going to right click on one of the data points and go to add trend line. And let's just start off with a linear. I'm going to click display equation and display R squared. So R squared tells us how well does the line fit the data. And you can see that our R squared value is 0.92, which 1 is perfect. So that's pretty close to 1. But if you notice, the line doesn't really go through any of the dots. It kind of splits the difference and gets there in the middle. So now let's right click on one of the points and go to add trend line. And now I'm going to pick exponential. And again, display equation and display R squared. And here we have an exponential equation, and our R squared value is 0.969. So that's better. And you can see that exponential curve, the curvy one, it actually looks like it goes through some of the points and captures the trend of the data better. So for this data, I would definitely use an exponential function to model it. So since we're going to use an exponential, I'm just going to delete. It's going to let me delete it? I don't think it'll let me delete my linear. I'll just get rid of the... Oh wait, there we go. So got rid of my linear. So now I just have my exponential because it looks much better. So in our exponential function, let me just type it in here. It tells us that y, which we could represent by q of t, or quantity, is 2.677 e raised to the 0.3202 times x, which is our input variable. I'm just going to use t. So let's compare the standard form that Excel gives us to the standard form that we use in your book. Your standard form is q naught times 1 plus r to the t. So these are different. Excel uses that little e. Little e is actually a number. It represents a very important number in math. Those of y'all that go on and take pre-calc or calculus, or especially something that deals with imaginary numbers, maybe you go into electricity, you use that letter E a lot. Its value is, I think it's like 2.71782 something. It goes on forever without repeating, kind of like pi. So E is a very specific, irrational number. And it's so special, mathematicians use the letter E for it rather than trying to write it out. So these are both two forms. They're different, and we want to be able to convert from Excel into what the book uses. So I'm going to rewrite Excel's form just so we have something to reference. Q of t is equal to, I'm going to write it as a times e raised to the k t. Just again, I'm just picking some letters so we can kind of compare. But our book uses q naught times 1 plus or minus r to the t. Excel uses a times e raised to the k times t. So in both of these, the first number is our initial value. So in both of these forms, q naught is actually equal to the a. So looking at Excel's formula that it gives us, our initial value is the number that comes first. That's the same as our q naught, which is the same as 8. That's 2.677. So we're saying that Compaq in 1990, according to this model, did $2.677 billion in revenue. So that first number is the same. Now, to convert between the whole 1 plus r and the e to the kt thing, we've got to do a little bit of algebra. So you may or may not remember from an algebra class that a number raised to multiplication is actually equal to that, in parentheses, that number raised to the first thing raised to the second. So it's just a fact, you may or may not have seen it, that e raised to the parenthesis k times t is equal to e raised to the k raised to the t. Again, that's just a math fact. But we're going to use that to do our conversion. So e is a number, it's 2.717 something or another. K is a number. If we take a number and we raise it to a number, we get another number. So I'm going to convert my e raised to the k times t. I'm going to rewrite that as e to the k to the t. So I'm just going to come down here. So I'm going to rewrite what we have in Excel. In Excel we have e raised to the 0.3202 t. Let's rewrite that as e raised to the 0.3202 raised to the t. So again, e is a number, we're raising it to a number. That's going to have a value. The way we get e raised to the 0.3202 in Excel is we use the exp function. And this one's a little bit funny because we don't actually put in the raised sign. We just write equals exp parenthesis 0.3202. And when I do this, when I hit enter, that's going to evaluate e raised to the 0.3202. And again, it's a little bit funny, you're not putting in the caret to actually raise it. The exp function knows that it's e raised to that number. So that's how we put that into Excel. So we see that e raised to the 0.3202 is equal to 1.3774. So what we did is we just converted e raised to the k times t to now we have it in the form, where can I write this? I'll just stick it maybe up here. Now we have it in the form q of t equals our initial value, which is still 2.677 times, and again, e to the 0.3202 is equal to 1.3774 raised to the t. So we just converted it from Excel form with the e into closer to what your book uses. And the last thing we have to do is convert it from the 1.3774 into the 1 plus r form. So if you take that 1.3774 and just think about pulling an r, or pulling a 1 out of it, would you agree that this is equal to, just write it beside it, q of t equals 2.677 times 1 plus 0.3774 to the t? Do you agree that this equation and this one are equal? So that tells us that our growth rate is the plus number, which is 0.3774. So we can say that our growth rate, since it's positive, it's adding, that's going to be 37.74%. So again, what we just did is we converted from the Excel form with the e. We used an algebra fact that e raised to the k times t is equal to e to the k raised to the t. E to the k is a number, so we use that exp function down here in Excel. We did e to the 0.3202, and again in Excel that's equal exp parenthesis 0.3202 to get that number. So that rewrote our function as 2.677 times 1.3774 raised to the t. And then I just separated the 1.3774 into 1 plus 0.3774 so we could see our rate. And since it's plus, that tells us it's positive. So our growth rate is 37.74%.